All right, let's jump right in. Today, we're going after a problem that has been a thorn in the side of mathematicians for centuries. How do you find the exact answer to some truly monstrously complex equations? We're going to explore a groundbreaking new method that honestly promises to solve the unsolvable.
Just take a look at this beast. It's an 18th degree polynomial. Let that sink in. The question is, where would you even begin to find its exact solution? For a very, very long time, the answer from the world of mathematics was pretty simple. You couldn't. You see, for centuries, equations like this, these high-degree polynomials, were kind of the villains of algebra. The higher the degree, the more ridiculously complex they get, and finding their precise roots, well, that was considered a monumental, if not a completely impossible challenge. So why? What was the big roadblock? Well, it really comes down to the fundamental limits of classical algebra. You've got these famous theorems, right, like Abel's theorem, which basically prove that you can't solve general polynomials of degree 5 or higher using simple formulas. So for ages, mathematicians had to find workarounds, but those workarounds came with a huge catch.
And that catch is what I like to call the approximation trap. The traditional methods for tackling these equations, things like Newton's method, they don't give you the perfect answer. Nope. They give you an estimate, a close enough value that's often riddled with rounding errors and, honestly, can be totally unreliable when things get really complex.
And the difference here is, well, it's night and day. On one side, you have the old ways. You're dealing with estimates, rounding, and a constant risk of errors. But on the other side, there's this new path proposed by Murad Sultan Ezouidi's theorem that promises something absolutely revolutionary, exact, symbolic, and completely error-free answers.
So, this is where our hero, Ezouidi's theorem, finally enters the scene. And what's so cool about it is that it doesn't just try to tweak the old methods. No, it throws them out entirely and brings in a completely new, systematic process for finding these perfect solutions.
And hey, don't just take my word for it. In his own words, Murad Sultan Ezouidi says his method bypasses all those old limitations, providing precise roots for equations that everyone else had written off as unsolvable. It's a bold claim, a direct challenge to centuries of mathematical thinking.
Now, to really get this, we have to understand what a symbolic root actually is. Think of it this way. An approximation, or an estimate, is like a blurry sketch of a key. It might look right, but it won't open the lock. A symbolic root, on the other hand, is the perfectly cut, exact key. No rounded edges, no decimal guesswork, just the pure mathematical form that fits the lock perfectly. So while the full formula might look a bit intimidating, it's really built on three beautiful core ideas. First, you have binomial coefficients, which act as the systematic adjusters in the calculation. Second, there's a base coefficient, which is kind of the anchor for the whole process. And third, and this is the real magic here, is recursion. Each step uses the answer from the one before it to build the solution piece by perfect piece.
All right, enough theory. Let's see this thing in action. We're going to take that monster 18th degree polynomial from the beginning and watch as this theorem just systematically dismantles its complexity, step by step.
Okay, so the process begins. The theorem gets to work calculating a series of symbolic coefficients. For the first value, k equals 0, what do we get? A nice, simple result, 0. One piece of the puzzle just vanished. On to the next step. For k equals 1, the formula does its thing, it churns through the numbers, and again, the result is 0. A pattern seems to be emerging here, doesn't it?
And this pattern just kicks into high gear. For k equals 2, 3, 4, all the way up to 7, every single one of these coefficients turns out to be 0. You can almost feel the equation getting simpler with each pass, as the theorem just clears away all the noise.
And then we get to k equals 8. And here, something different happens. Bam! We get our first non-zero value. This is a critical piece of our final puzzle, the first major term of our brand new simplified equation.
But right after that breakthrough, the simplification pattern comes back with a vengeance. The coefficients for k equals 9, 10, all the way up to 16, they all resolve back to 0. More and more of the polynomial's insane complexity is just dissolving away.
And that brings us to the very last step. For k equals 17, we find our second and final non-zero component. This complex number right here is the last piece of the puzzle we need to finally construct the exact answer.
Okay, so let's move to the grand finale and see how all of this comes together.
After 18 recursive steps, where most of the terms just zeroed out, we can finally see just how much simpler this once impossible problem has become. Just look at that. Remember that terrifying multi-line beast from the beginning? It has been boiled down to just 3 terms. All of that incredible complexity has been distilled into this elegant, much, much simpler form. That right there is the power of this symbolic method. And from that simplified equation, we get this. The exact symbolic root. Now, I know what you might be thinking. That still looks pretty complicated, right? You've got square roots, exponents, the imaginary number I. But here's the beautiful part. Every single symbol you see there has a precise absolute meaning. This isn't an estimate. This is the perfect answer found through a clear, repeatable process.
So, what we've seen here isn't just a clever new formula. It's a fundamental shift in how we can think about solvability itself. And that's the real takeaway. An equation that was once considered impossible can now be solved with perfect precision. What does that mean for other fields? Think about quantum physics, fluid dynamics, or advanced engineering, all fields where these kinds of equations model incredibly complex systems. Problems that always had to rely on good enough approximations might now have exact answers, and that could unlock a whole new level of precision and understanding. So the question isn't just if we can solve it anymore, the real question is, what other impossible problems are now within our reach?